we started simple harmonic motion with a linear spring that we described with Hooke's law, F equals minus kx. And what I mean by linear, you can see if we plot the force as a function of x, and you can see it's a line like this, goes through the origin with a slope of minus k. This is the point of stable equilibrium where the force is 0. If you move this way, it pushes back. If you move this way, it pushes back. That's why we have oscillation around that point. So the force is linear with x, but what linear here really means is when we wrote the equation of motion, we got that minus kx equals mx double dot. So our equation of motion is also linear. Okay? Now, not everything in the world is linear. Most things actually aren't quite linear. So let's see what happens when we go to a nonlinear spring. And I'll just make one up. Let's say F equals a constant times 1 minus e to the bx. That could be a spring because if I plot that function, it looks a little bit like this. If this is f and this is x, it kind of comes and curves down like that. Okay? So clearly the plot is nonlinear. If we write the equation of motion, we get, let's see, c 1 minus e to the bx equals mx double dot. And now we have a nonlinear equation of motion. I want to be clear about what I mean. When you say the equation of motion is linear, you mean the function that you're looking for, x, is always here to the first power, and all of its derivatives are here to the first power. So this is a derivative with respect to time, but it's to the first power. If we had x dot, that would be the velocity, and if it's to the first power, then the thing is linear, right? So this is linear, x double dot. Here, we have a nonlinear equation of motion, okay? X double dot is linear, but here we have x, and it's under an exponential, e to the x. So that's what makes it nonlinear. This is really important because a linear equation of motion we already solved because you just guess, right? We can guess something. So what function is equal to its own second derivative within a constant or two? Well, we came up with 4 of them, right? Sine, cosine, e to the x, and 0. Here you'd say, what function is equal to, let's see, when you exponentiate the function and then subtract it from 1, it's equal to its own second derivative to within a constant. That's a harder guess. And it's more than just a harder guess, it's a nonlinear differential equation. So there are special techniques to deal with nonlinear differential equations. It's beyond the scope of the course, and it's also beyond the scope of what physicists usually like to do. Okay? We have a different solution to this problem. What we do is say, okay, in my experiment, I promise you I will stay in this box. Right? We control the experiment, we control x. I'll never leave this little domain of x. Or maybe you like the origin. You say, I promise, absolutely, I will not go more than this far in plus x and this far in minus x. Or maybe you like big slopes. Maybe you're going to come over here and say, I will not leave this domain of x. So if you just consider a small domain, it actually looks linear, right? If we call this one A, and then make a plot of f versus x, you can see it's a fairly low slope like that. Okay. If we call this one B, that's right through the origin, and if we were going to make a plot of that one, it also looks linear like that. So by considering a small domain, we actually treat a piece, a little piece, that's basically linear. And then we can go back to these kind of solutions. Okay? So in this unit, what we're going to see is mathematically how we do this. How do we take a complicated nonlinear problem and linearize it and make it linear with some approximation.